Hello. In this lesson, we are going to build a complete Bayesian optimization framework from scratch using Python. The idea is to really understand how it works under the hood. No black boxes, no shortcuts. We'll start by defining the problem we are trying to solve, which optimizing expensive or noisy functions where gradient-based methods either don't apply or just are not reliable. Bayesian optimization is a solid choice for this kind of task because it uses probabilistic model, usually Gaussian process, to make smart decisions about where to evaluate next. And instead of brute forcing the solution, it builds a model of the function, balances exploration and exploitation through an acquisition function, and picks the next point based on what seems promising. So we'll go through the core components step by step, building them out in code, and by the end you will have a working optimization tool that you can actually use on your own problems. And I think that's okay, and I hope we can start now. So here's the libraries. You can see NumPy here, and what we have. Norm from SciPy stats for Gaussian CDF and PDF, and minimize from SciPy optimize, which we will use later to find the next base point based on the acquisition function. We are also putting in matplotlib pyplot for plots, and then from scikit-learn we bring the Gaussian process regressors and few common kernels, matter, white kernel, and constant kernel. Now let's take a look at this class. It's called Bayesian Optimization, and this is where all the logic for the optimizer will live. So we start with the init method. This is the constructor. Basically, it's setting the things up. You pass in the function f, you can see, which is the black box function we are trying to minimize. Then you provide bounds which define each space for each variable, kind of like saying, okay, I want to explore the function in this specific region. You also decide how many random points you want to sample in the beginning using an init. Here you can see that's useful because the Gaussian process model needs some initial data to get started. Then there is acquisition function parameter. By default it is set to EI, which stands for expected improvement, but you could also pass in UCB or POE if you want to use upper confidence bounds, or probability of improvement instead. We'll cover those later. That's okay. And next there is a kernel argument. This is optional. If you don't pass anything, it will fall back to a default. And finally there's alpha, which is just a small value added to the diagonal of the kernel matrix. That helps with numerical stability when we are fitting the Gaussian process. Now inside the method we store all these parameters as attributes on the class, the function f, the bounds, the number of dimensions, how many initial points to sample, and which acquisition function we are using. Alright, so if the user didn't pass in a kernel, we define a default one. So this default is a matter kernel with new equal 2.5, which allows for once differentiable functions. That just means the model assumes the function is fairly smooth, but not perfectly. We also multiply it by a constant kernel to let the model scale the output as needed. And then we add a white kernel with a small noise level. You can see, and that white kernel helps the model handle noisy observations, like if our function includes some randomness. Then we set up the Gaussian process regressor itself. We plug in the kernel, pass in alpha, and set the number of restarts for optimizer to 10. That restart part just helps the GP training avoid local minima when fitting hyperparameters. We also normalize the target values. You can see. That's okay, and it usually helps the model train better, especially if the output scale varies a lot. That's done, and below that we are initializing some variables to track what the model has seen. So x observed and y observed will store all the points we have evaluated and their corresponding outputs. At the start, both are set to none, you can see. Okay, we also track the best solution we have seen so far. Best x is the best input point and best y is the lowest objective value we have found. Since we are minimizing, we start best y at positive infinity. And you will see history. That's where we will store details from iteration, like what point was evaluated, what the result was, and what the best point is at that stage. It's helpful for plotting or analysis later on. I hope you understood what is this. Okay. Now let's look at how the acquisition function is calculated, and this is done inside the acquisition method. So this method takes a point x, the Gaussian process model, and the best objective value we have seen so far, that's best y. And okay, the first thing it does is reshape x to make sure it's a two-dimensional array, because that's what the GP expects. Then it asks the Gaussian process to predict the mean and the standard deviation at that point. That gives us two pieces of information: the model's best guess for what the function might output there, and how uncertain it is about that guess. I hope it's okay, and reshape is done. Now if the standard deviation is 0, what's happening? I mean, meaning the model is completely confident about its prediction. We return 0 right away. That point has no improvement potential because the model thinks it knows everything about it. Then, depending on which acquisition function we are using, it calculates a different kind of score. And if it is EI, which stands for expected improvement, we compute a z-score, you can see here. That's the gap between the current best value and the model's prediction divided by the uncertainty. The EI formula combines two things. What are they? How much better we could do compared to the base value so far, and how uncertain the model is. It's a balance between exploitation and exploration. If you are using QCB, which is upper confidence bound, well, technically here it's more like a lower confidence bound because we are minimizing. Then we take the mean and subtract kappa times standard deviation. The kappa value controls how much weight we give to exploration, and here a bigger kappa means we explore more uncertain regions. And finally, if we are using POI, which is probability of improvement, we again calculate Z and just return the CDF. So basically the probability that this point will improve on our best result. That's okay. If we pass in something else that's not 1 or 2, 3, the method just rises an error. That's a safeguard. Okay. Now that we have a way to evaluate the acquisition function, the next step is find the point that gives the highest acquisition score. That happens in the optimized acquisition method. So here's what this method does. It wants to find the x that gives us the biggest acquisition value, in other words, the most promising spot to evaluate next. We set up a loop with multiple random starting points. Why? Because the acquisition function is not necessarily convex. There might be multiple local maxima. So we start the optimizer a few times to avoid getting stuck in a bad spot. I I hope you understood, and let's look what's happening. In each iteration here, we sample a random point within our bounds and use SciPy optimize minimize to find a nearby maximum. And what's happening here? Here is a trick. Minimize does minimization, obviously, so we take the negative of the acquisition function. That way, minimizing the negative is the same as maximizing the actual acquisition score. That's okay. And we pass in the bounds and use the LFBGSB algorithm, which is good for box constraint optimization, meaning it respects our variable limits. That's okay. This part is done, and if the result of the current optimization is better than anything we have seen so far, we update best acquisition and store the corresponding point. At the end of the loop, we return the best x. We found that's the one with the highest acquisition value, and that's where we will evaluate the function next. So yes, that's pretty much it, and let's continue. Now we are at the main part. This is the optimize methods, and this is where the optimization process actually runs. When you call this method, you can pass in how many iterations you want to run. By default, it's set to 50. You can also toggle the verbose flag to print the progress during the run, and there is an optional callback if you want to hook into each iteration, maybe for logging or visualization. That's okay, I hope. And so the first thing it checks is whether we have already observed any data. If not, and usually at the beginning that's the case, it samples some initial points randomly from the search space. These are just uniform samples within the bounds we set earlier. Then it evaluates the objective function at those initial points and stores the results. This gives the Gaussian process something to work with. It can't model anything unless we give it some data to start from. That's okay, I hope. Next, we figure out the best result from these initial points, and we use argmin. You can see here argmin to find the index of the smallest y value. That's our current best guess for the minimum, and we store both the input x and the function value y. And okay, if verbose is on, we print that initial best observation just so we know where we're starting from. Now we enter the optimization loop, main loop here. This runs for however many iterations you have asked for, and in each iteration we do a few things. First, we fit the Gaussian process model to all the data we have seen so far. That includes the initial random points and any points we have added in previous steps. The GPU learns from this data and updates its internal model of the function. Then we ask the acquisition function where to go next. This is where optimization acquisition comes in. You will see here, and it returns a new x that looks promising based on the acquisition score. We evaluate the real objective function at that new x, which gives us actual y value. Then we update our dataset, we add this new point, and it is a result to the list of observations. So next time we fit the GP, it will take this point into account too. Now comes an important part. We check if the new y value is better than the best one we have seen so far. If it is, we update our best known x and y. And again, if verbose is enabled, we print either a message about a new best value or just the result from a current iteration. And every iteration also gets logged to the history list. You can see this keeps track of the iteration number, the evaluated point, its result, and current best result. It is useful if you want to make convergence plots or analyze how the optimization evolved over time. And finally, if a callback function was provided, it gets called with the current state of the optimizer. And at the end of the whole loop, we return the best point and best value we found during the process. Okay. Now visualization time. We'll start with the plot convergence function, and this one's pretty simple. It just shows how the best value found by the optimizer changes over time. So if you are wondering whether the optimization is actually improving anything, this plot will make that clear. First, it checks if there is any history to plot. If not, maybe the optimizer hasn't been run yet. It prints a warning and exits. Then it goes through each recorded iteration and builds a list of best values. If the most recent value is better than the one before, it adds it. Otherwise, it just repeats the last best value, and that way we get a stepwise curve that only moves when we actually find a better solution. And we use matplotlib to plot it. The x-axis is the iteration number and the y-axis is the best objective value seen so far. The label shows up in the legend, so it's clear what the curve means. Now let's look at plot acquisition. This one is a bit more involved because it handles both one dimension and two plots. Two-dimension plots, and those require different kinds of visualization. First, check here is important. It only works if the number of dimensions is 1 or 2. So if you are working in higher dimensions, it just exits and tells you that plotting is not supported. Once that's out the way, fits the Gaussian process model to the current data. This makes sure we are always plotting the most recent model. If we are in one dimension, we create a grid of evenly spaced x values across the domain. Then we ask the GP to predict the mean and standard deviation at each of those points. With that, we can do two things. What are they? We can plot the models predictions along with the uncertainty, and we can compute the acquisition function values from those same points. The first plot shows the surrogate model. And what is that? This thing. We draw the predicted mean as a blue curve, and you can see, and we will fill the region around it with two standard deviations in each iteration to show the model's uncertainty. We also plot the observed points in red, and we draw a horizontal line for the best value seen so far. Then in the second plot, we draw its values across the same grid, and we mark the next point to evaluate with a vertical dashed line, and that gives a sense of where the optimizer is planning to go next. And I think that's okay. And if we are in two dimension, the plotting is a bit more complex. So what's happening? We start by building a mesh grid from to one dimension least space arrays. This gives us a grid of x1, x2 coordinates across the whole search space. Then we flatten that into a list of points because the GP expects two-dimension inputs. Next, we calculate the acquisition function at each of these points and reshape the results into a grid again. That's so we can use it for contour plots. That's okay, and I hope you understood what's happening here. Contour is okay, and we calculate the acquisition function at each of these points and reshape the results into a grid again. That's so we can use it for contour plots. I say that, and we also predict the mean output at each point, so we can show that the GP believes about the function overall. That's okay. And before the example, the first plot in this case is a contour plot of the predicted values. Darker areas are low predicted outputs and lighter areas are higher. We overlay the observed points in red and we mark the best observation with a gold star. In second plot, we draw a contour plot of the acquisition function itself. And again, we mark the next evaluation point with a red cross. So just like in one dimension, this gives a clear idea of what the model knows and where it's planning to go next. Both plots get color bars, axis labels and titles, so everything is readable, and we wrap it up with tight layout to clean up spacing. Example time. Here we define a simple one-dimensional objective function. It's a combination of a squared term and a sine wave plus some noise. So it's nonlinear and a bit noisy, which is perfect for testing Bayesian optimization, since that's the kind of problem it's designed for. Then we set the bounds. You can see we are saying search between -1 and 6. That's where we think the minimum might be. Next, we initialize optimizer. We pass in the objective function, the bounds, and we ask it to start with 5 random samples. We are also using expected improvement as the acquisition function. You can see here EI. Then we run optimization for 15 iterations. Each iteration will evaluate one new point, update the Gaussian process, and pick the next point using the acquisition function. Once that's done, we print the best input and output values found. That's okay, and then we plot the results. The convergence plot shows how the base value changed over time, and the acquisition plot helps us see what the model looks like, including the surrogate function, the uncertainty, and where it plans to sample next. So here's two-dimensional example, and this one is a little more complex. The objective function here depends on both dimensions. It's sine product over x and y divided by x multiplies y with a bit of Gaussian noise added in. So it has a few local minima, and the scale changes a bit our domain. And you will see bounds we define for both dimensions. Each goes from 0,1 to 4.0. Then we set up the optimizer again. This time we ask it to start with 10 initial random samples, and we are still using EI for the acquisition strategy. And the optimization is run for 20 iterations, a little longer since it's working in 2 dimensions and the space is larger. And again, after it finishes, we print out the best result and shows the plots. We reduce the resolution of the acquisition plot slightly, just to speed up rendering. In 2 dimension, that acquisition plot becomes a pair of contour maps, one for the GP's predictions and one for the acquisition values. And at the very bottom, we have got inf name main block. So if you run this script directly, this is where you would call one of the example functions. Let's look at outputs, and let's start with the logs. These lines are just printing out what happened at each iteration, So on the first line, you see the initial best result. That's one of the randomly sampled points before the optimization loop began. Its value was around -0.41. Then from iteration 1 onward, it starts sampling new points. Early on, the objective values are mostly floating around -0.2, -0.1, not particularly impressive. Around iteration 7 though, something better shows up, and you can see the optimizer picking up that and slowly honing in. By the time we get to iteration 15, there is a big shift. It finds a point at 0 0.1, 0 0.1 with a value of negative 8.85, and that becomes the new best. That's a massive improvement. From there it keeps evaluating more points, but nothing beats that one. So 0 0.1, 0 0.1 ends up being the final result. Look at here. This is showing us the best objective value found so far at each iteration. So initially it's flat, nothing much is improving. Then around iteration 13 or 14 it starts dropping. At 15 you can see we get that big jump. After that the curve flattens out again, which tells us the optimizer hasn't found anything better since. And okay, let me zoom out. That's okay. These are probably the most informative ones. On the left we have got the Gaussian process surrogate model. This is the model's prediction of the function surface based on everything is learned so far. The red dots are all in the here are all the points it's actually sampled. The yellow star here you can see here. What is that? Any idea? This marks the best observation, and that's the 0 0.01 right point we saw in the logs, and the color scale tells us what the model is predicting. Lighter areas are higher values and darker areas are lower, so we are trying to push toward the dark blue areas if we are minimizing. Then on the right is acquisition function, in this case expected improvement, right, EI here. This shows where the model believes it might be worth sampling next. You will notice most of the acquisition values are very low, almost flat we can say, which means the model is pretty confident it's already found a good spot, and the red X is where it's planning to go next if we were to keep optimizing. But given how flat that EI surface is, it probably would improve much unless we add more noise or change the kernel. The model seems fairly certain it has already found the minimum. So overall, this run looks solid. The optimizer started out exploring, then locked in on the 0 0.1, 0 0.1 region, and it didn't waste too many iterations once it found a good value. The acquisition surface confirms that there is not much incentive to keep going unless we want to retune things or explore further.